Rational functions, this is section 2.6 from our text. This is part 3, and this will be our last piece. This is the final piece to rational functions. Yesterday we finished with this function. We called it g of x, which equaled x cubed minus 3x squared minus 4x plus 12. And that was all with a denominator of x plus 1. So you can recall from your notes a lot of what this function was characterized by. We could factor by grouping. We got x minus 3, and then we had an x plus 2, x minus 2 over an x plus 1. That would yield negative 1 as a vertical asymptote, positive 3, positive 2, and negative 2. And so it's x equals negative 1. We had a y-intercept here of 12. And we sketched our graph based on that information. Also with this information of an n behavior model. And we looked at x cubed over x, which simplified to be x squared. So we said that x squared, way out to the left, this is g of x now, not f. Way out to the left, g of x went up to positive infinity, and way out to the right, g of x also goes out to positive infinity. We said then that there is no horizontal asymptote. All right, that's important information, and it is still highly relevant, but today we're going to get a little bit better with our message here. Right, so we're going to cross at 3, cross at 2, and we've got an image that looks roughly like this. We had taken a peek at what this looked like graphically. Here it is. This is a slightly zoomed out version of that function g of x. We'll come back to that in a second. We're going to clean up our n behavior model today, and we're going to make it a little bit better. So if I put y equals x squared on this graph, you can see that the black and the green, similar to the right and to the left, the black and the green are both going up to positive infinity, but we're going to do a little bit better than that today. So we're going to come up with a better n behavior model. We're going to come up with what we'll call a slant asymptote. A synonymous word here, a term, would be an end behavior asymptote. And these are going to occur when the numerator has a greater power than the denominator, greater degree. All right, so the numerator degree is greater than the denominator degree. That's not what I wanted. So how do we clean up and make our n behavior model better? Well, we're going to use synthetic division. We're going to simply do the division problem that is stated in our function. We're going to take x plus 1 as our divisor. So I'm going to use synthetic division with a negative 1. I'm then going to use my coefficients of 1, negative 3, negative 4, positive 12. Synthetically divide, add down, and we get a 12 here for a remainder. This 12 for a remainder tells us that x plus 1 is not a factor of the numerator. We knew that already because we had already factored the numerator and we did not find an x plus 1. That 12 helps confirm that. But what we have said now is that g of x could be written as this quotient, x squared minus 4x plus 0, plus a remainder 12 over x plus 1. Right? That function is exactly the same as the function that we have written up at the top. Those are exactly equivalent. So what we're going to say is that our n behavior asymptote is this quotient. Our n behavior asymptote, or our slant asymptote, is going to be the function y equals, actually I'm going to call it e of x, just for n behavior. It doesn't really matter here. E of x equals x squared minus 4x. So if I go back over to the graphs, here's my green, which was g of x. Here's my e of x, and you can see that e of x in blue very closely models the green g of x. unlike x squared, where they're close, these two have a lot of precision here, e of x and g of x. So that's going to be our end behavior asymptote. It's better than x squared. It will still have the same end behavior ending up and up. The limits are not changing, but our end behavior asymptote will be a little more precise than just x squared. The second thing we're going to talk about today, besides slant asymptotes, is an x-intercept bounce. We've discussed that loosely before, and a vertical asymptote where both sides go the same way. All right, so what I mean by that is if I have some vertical asymptote, we'll use a vertical asymptote here of positive 3. Typically, I've stated that our graphs, if on one side of the vertical asymptote they trend up, on the other side they're going to trend down. But what's that 0.1% of the time where they don't? Right? Think about where that might occur. It might be easier to start here with an x-intercept bounce. Right? If we had a function, we'll call this function h of x, which equals x minus 2 squared over x plus 1, we would know that that function has an asymptote at -1. We also would know that this function has an x-axis intercept of positive 2. But what happens at that positive 2? Does this function cross at positive 2 or does it bounce? And this function is actually going to bounce. And it has to do with that double root, the fact that the factor of x minus 2 comes up twice. If we plug in 0 for the x values, we would get our y-intercept to be a positive 4. And our graph is going to look something like this. The end behavior model will be based on an x squared over x. It'll be like y equals x, and it'll go up to the right and down to the left. And our graph would look like this. But the key feature that I really want us taking out of this is the bounce at positive 2 and the fact that we have the duplicate root, the double root, in the numerator. So what's that look like over here on the right? We'll call this function we'll call this function k of x, which equals, I'm not going to call it k of x. I'm going to call this function f of x, which equals 1 over x minus 3 squared. Here we see that double root occur in the denominator. Well, the denominator sets our vertical asymptotes. Because of that denominator having a double root, we're going to end in the same direction on both sides of this. To take a look at the official graphs of these, and go back to my Desmos, I'll turn on, this is h of x, which has the x minus 2, that quantity squared. We can see that that graph is going to bounce at a positive 2. F of x is going to have a vertical asymptote at x equals positive 3, and we can see that this graph on both sides is going to trend up and up. Something to hold on to. All right. I'm going to leave you with a function today that I want you to think about. I want you to consider. You can graph it using Desmos. You can graph it using your calculator. But I'm going to give you the factored form of k of x. X plus 3 squared times x minus 1. X minus 2 squared times x plus 4 will be our denominator. What would that graph look like? Where might the graph bounce off the x-axis? What vertical asymptote might we not change sides? How would that image be put together? Feel free to check it using your graphing calculator. Feel free to check that using Desmos or something of the like. Take care.